Hello everybody, welcome to this next video on numerical analysis. In this video we will talk about order of convergence of a method. Okay, so what we have done till now, we have done bisection, we have done Newton, we have done fixed point method, we have done secant method, and we would like to now compare these methods. So this is a general trend. Whenever we have 3-4 things for doing the same thing, that is f of x is equal to 0, all these things 1 2 3 bisection, fixed point, Newton and secant, they are finding out the roots of f of x is equal to 0. So obviously there is a need to compare these methods, that which one is better in which sense. So for that, the first for comparison, the most important thing for comparison is the rate. Important thing is the rate at which these methods converge. So we would like to know, we would like to have a mathematical criteria to find out this convergence rate. So that is basically your order of convergence. So we have this order of convergence. What is order of convergence? So you see, every method, whether it is bisection, Newton, fixed point or secant, what it is doing, these methods, they are generating a sequence P1, P2, P3, P4 and so on, and this sequence ultimately converges to P, and this P is your exact root. This P is your exact root. So what we are doing are these methods, they are generating a sequence, which sequence is converging to the exact root provided some conditions are satisfied, and we assume that all those conditions are satisfied. Correct. Now we would like to know how fast this sequence is converging to P. For that, what we are doing, suppose P is your exact root and P naught is your first initial guess, then P1, P2, P3, P4, and at this point if you subtract with P, this is your error, E naught. Your exact root, subtract from the iteration, this is your E1, P, this is E2, and this is E3, and this is E4, and so on. So basically E5, En is error at nth iteration. Okay, and because you are saying that the sequence converges to P, it means that we expect that error is decreasing, then only ultimately you will reach to P. So this is what we expect for a convergent sequence. So it means that we expect that E5 is less than E4, is less than E3, less than E2, less than E1, E6 less than, and so on. This is what we expect. Now, if suppose E1 is 10 to the power minus 1 and then E2 is of the order 10 to the power minus 3, you have one this sequence, and another is E1 is equal to 10 to the power minus 1 and E2 is equal to 10 to the power minus 10. So obviously this trend, if you have a sequence of errors with this trend and another one is with this trend, then this is faster as compared to this, because here you see at E2 you reach to 10 to the power minus 10. Here at E2 you have just reached to 10 to the power minus 3, starting with the same initial guess. So for defining these things, we have this thing ki if error at n plus 1th step upon error at nth step raised to power alpha, this is in the limiting case, because we in the beginning this may not happen, if this is equal to some constant lambda. If this is equal to, this quantity is equal to a non-zero positive constant, then alpha is called order of convergence. This is the definition, called the order of convergence. This is called the alpha is called the order of convergence. This is the definition of order of convergence. Let us analyze this thing. It means that if alpha is equal to 2 and suppose alpha is equal to 1 and your En is say 10 to the power minus 3, then E3 is 10 to the power minus 3. If you forget about this limit, then E4 upon E3 raised to power, in this case e raised to power 2 is equal to lambda, and here you have E4 upon E3 raised to power 1 is equal to lambda. It means that here E4 is equal to lambda into E3. E3 is 10 to the minus 3 raised to power 2. Here E4 is equal to lambda E3. Here E3 is 10 to the minus 3. Same. 10 to the minus 3 raised to power 1. So you get E4 is lambda 10 to the minus 6. Here E4 is lambda 10 to the minus 3. So you see, if alpha is more, it means that order of convergence is more, error will decrease faster. You see, E3 was 10 to the minus 3, then E4 is 10 to the minus 6. Here E3 was 10 to the minus 3 and E4 is still of the order 10 to the minus 3. Slowly it will decrease. And here there is no condition on lambda, but if alpha is 1, that is your alpha is 1, order of convergence is 1, then lambda has to be less than 1. Because if lambda is greater than 1, then it means that if alpha is equal to 1 and lambda greater than 1, it means that En plus 1 is equal to lambda into En. This is greater than En. So you have a sequence increasing. So convergence cannot happen. So let me write down the definition again. Order of convergence is if limit n going to infinity En plus 1 upon En raised to power alpha is equal to lambda, this should be non-zero, then alpha is called order of convergence, If alpha is equal to 1, we call it a linear convergence, and for here lambda should be less than 1. This is the condition on lambda, because otherwise it is not a convergent sequence. If alpha is equal to 2, we call it as a quadratic convergence. Here lambda can be anything, right? So this is the order of convergence. Now we would look at an example to see how alpha is equal to 1 and alpha is equal to 2 will affect the convergence. So let me give you an example. Suppose you have a sequence Pn. Suppose there is a sequence Pn converging to 0 with lambda is equal to 0.5, starting with P naught equal to 1. This is one. And another, suppose there is another sequence Pn tilde converging to 0, starting with P naught tilde is equal to 1 and lambda is equal to 0.5. Same. So let us write down these two sequences. The first sequence is this Pn sequence is Pn, because it is converging to 0, Pn minus 0 upon Pn minus 0 is equal to lambda, which is 0.5. This is in the limiting case, but let us approximately write it. Pn minus 0 upon Pn minus 0 is equal to 0.5. Sorry, Pn plus 1 here. This is by the definition of order of convergence. Definition of order of convergence. And the second sequence is Pn plus 1 tilde minus 0 upon Pn tilde minus 0 square is approximately equal to 0.5. So here you have, here you have Pn plus 1 tilde upon Pn tilde square is equal to 0.5. And here you have Pn plus 1 upon Pn is equal to 0.5. So you start with the P naught is equal to 1 here. So your P1 is going to be 0.5 into P naught. So this is equal to 0.5. Then your P2 is going to be 0.5 into P1. This is going to be 0.25. Then P3, which is 0.5 into P2. This is 1.25 into 10 to the power minus 1. P4, which is 0.5 into P3. This is equal to 6.25 into 10 to the power minus 2. And I'll just write down P5 is going to be 3.1250 into 10 to the power minus 2. P6 is going to be 1.5625 into 10 to the power minus 2, and P7 is going to be 7.8125 into 10 to the power minus 3. Okay, now let us go to the another sequence. Here we have Pn plus 1 tilde is equal to 0.5. I am assuming that the sequence is of positive numbers. So this is the situation. So you start with P0 equal to 1. P1 is going to be 0.5 into 1 square. So this is 0.5. P2 is going to be 0.5 into P1 square. This is going to be 1.25 into 10 to the power minus 1. P3 is 7.8125 into 10 to the power minus 3. P4 is equal to 3.0518 into 10 to the power minus 5. P5 is 4.6566 into 10 to the power minus 10. P6 is P6 here is 1.0842 into 10 to the power minus 19, and P7 is 5.8775 into 10 to the power minus 39. Now you see the difference here. If your sequence is converging linearly, P7 is 10 to the power minus 3, and here if your sequence is converging quadratically, your P7 is 10 to the power minus 39. Both are converging to 0. So you see at 7th iteration, if the sequence is quadratically convergent, you are very close to 0, almost 39 digits. And if the sequence is linearly convergent, you are very far away from 0. You have only 0.0001, something like that. So we would like to have methods which are quadratically convergent as compared to methods which are linearly convergent. So it should be clear that how this alpha is decreasing the error for the sequence. And I would also like to comment this lambda is called asymptotic rate constant, asymptotic error constant. If you have two methods, say for example, if you have two methods, both are with lambda is equal to 2, alpha is equal to 2. If you have two methods both with alpha is equal to 2, then the method with lower lambda is better, because there are two factors, en plus 1 is equal to lambda en raised to power alpha. So this method, this lambda and alpha both are playing roles, but alpha is playing a larger role in the convergence as compared to lambda. So if you have two sequences with same alpha, then lambda is your deciding factor for the rate of convergence.